Welcome to part 2 of our video on walking through the gradient descent with backpropagation process while training a neural network. To review where we're at, we are trying to calculate the new weight for EF, the new value for the weight of EF. And so to do that, we first we're applying this formula where the new value of EF is the previous value of EF minus the learning rate, which specifies how fast we update the weights in each epoch, times the partial derivative of the cross entropy loss with respect to the value of EF. And so intuitively, if the loss is high, we will change the weight value a lot, and if the loss is low, we're changing the weight value a little bit because it's already good. And so in order to actually calculate this, the partial derivative of the cross entropy loss with respect to EF, we need to apply the chain rule because we don't have this derivative directly. So applying the chain rule in calculus, we get that the partial derivative of the cross entropy loss with respect to weight EF is equal to the partial derivative of the cross entropy loss with respect to F times the partial derivative of F with respect to EF. And you can see this partial derivative of F up here and the partial derivative of F down here in the denominator cancel out. Okay, so to calculate this, we're going to first remind ourselves what's our cross entropy loss. So we're going to start with calculating this first term, the partial derivative of the cross entropy loss with respect to F. The cross entropy loss can be written in this way, the y true times log of y hat plus 1 minus y true times log of 1 minus y hat. Because y hat in the case of this neural network is F, we can just replace all instances of y hat with F, and that gives us this equation over here where log of F and log of 1 minus F. And so we're taking the partial derivative of this whole function with respect to F. So now we can just apply some calculus derivative rules, which ends up working out to this. We won't go into the details, but it's just your basic derivative rules from calculus here. Okay, so now we're trying, a reminder of where we're at. We're trying to predict the partial derivative of the cross entropy loss with respect to EF, which involves the multiplication of these two terms based on the chain rule from calculus. We just now calculated this term up here, which is this first term, is the partial derivative of the cross entropy loss with respect to F. So we just calculated that value in terms that we're familiar with. We know what the value of F is, that's what the output of the neural network is, and we know what y true is. So great, we have the partial derivative of the cross entropy loss with respect to F in terms of numbers that we definitely already have once the neural network makes a prediction. So great, that's progress. Next step is to calculate the second term, which is the partial derivative of F with respect to EF. And to do this, let's note that F can be written as EF times E plus DF times D. However, because we're taking the partial derivative with respect to EF, we don't care about this DF. It's going to be 0. So let's just ignore that for simplicity. So we could just think of F as EF times E, and because it's with respect to EF. And so if we take the partial derivative of F with respect to EF, we just get E. So the partial derivative of EF times E with respect to EF is E. Very basic derivative rules there. So putting that together, we now have our terms for this first term and the second term. So that's written out as this. And we also have the value of node E. We calculated that during the forward propagation, right? We know that E is just whatever BE times B is plus whatever AE times A is plus whatever CE times C is. And that was calculated up here. So we already know the value of E is 6. We previously calculated that on our way towards making the final prediction of 0.99 of the neural network. So this very reason, because now we need E, that's why we do the forward propagation first and then work backwards through the network to do the back propagation, because we increasingly use values of nodes that we previously calculated during the forward propagation. So now that we're here, we have our value of what we update the learning rate by. So EF equals, sorry, not what we update the learning rate by, what we update the value of edge EF by. So EF is equal to EF minus the learning rate times the partial derivative of the cross-entropy loss with respect to EF, which we calculated as this whole term here. And everything in this term now, Y true, we know what Y true is. F, we know what F is, that's the output of the node. E, we know what E is because that's the value of the intermediate node, that particular hidden node. So we can calculate EF in that way, and we can get a number, let's say negative 59, by just plugging in some values there. And now we have our new value for EF, which in this case is negative 59. This example was worked out just with one input, but you could imagine it's very similar when you have many data points working simultaneously. So that, and so last thing is, okay, we now have the new value for edge EF, and we can work through the network backwards in this exact same way, but now treat node E how we previously treated node F while we're calculating A, or the value of AE and BE and CE and all the other weights. So that's basically how backpropagation works in a neural network, and how gradient descent works in general, but in particular for a neural network. So I hope this was educational, at least providing the intuition, the mathematical intuition behind how stochastic gradient descent works, and in general how a neural network is trained. Really, it's just applied calculus. It's an algorithm that uses calculus to update edge weights so that the edge weights through each iteration of the algorithm get closer to edge weights that will match the true prediction from the predicted, the true value from the predicted value. So hope this was educational, and yeah, now you know all about neural networks. So in the next video, we'll talk a little bit about some different types of neural networks. It'll hopefully be a little bit less mathy, a little more relaxing. So stay tuned for that final video in this neural network series.